Hi, everyone. Thank you for coming. My talk today is going to be a big jump from the last one, which was an introduction and fun and cute and great. Mine is going to really cover some higher level astronomy. I'm trying to give it to the right audience, but just prepare yourselves for some big astronomy ideas. So he gave an introduction of me, but here's me with my telescope at Griffith, and this is also at Griffith. So, in my talk, I'm going to give an introduction to cosmology, a history of cosmology, our idea of what the universe really is. I'm going to talk about the amazing space telescopes that we have made in the last about 30 years that have been able to really shed so much light on the nature of the universe, near and far. I'm going to focus on the far and the big. And then I'm going to talk about the largest scale cosmic structure of the universe and how we observe it and how we theorize about it. So that should be very interesting if you can follow along. Hopefully I can get that done. So astronomers are inspired in all the same ways we are humans, and so we want to answer the big questions. Where did we come from? Why is the world the way it is? And where are we moving toward? And we focus our attention using our tools and our knowledge to create more directed questions that we can actually try to answer. So they turn into, what is the history of the universe? What does the universe look like today? What did it used to look like? And what does the future hold for our planet, our species, but all the way up to the entire universe? And we are scientists, and so we answer these questions with the scientific method. So we come up with hypotheses, and we create theories, and create models, and then and we use very creative thinking to do so. And then we need to test those theories with equally creative thinking and make sure that our theories are very robust by testing them in as many ways as we can think of to try to catch ourselves, because we're always trying to be right, but trying to catch ourselves being wrong just as much. So the way in astronomy we do that on the large-scale universe is we use cosmology, which is like a subclass of astronomy, which is the study of the laws, nature, the overall big picture of the universe. And we create these really complex cosmological models of trying to explain the entire universe in one model that all works. Very complicated. And then obviously our observations are done with telescopes. So now a history of cosmology. So we as humans, with our consciousness, we've always perceived the world around us, whether we like it or not. And we have pretty much for all of human history up until a couple hundred years ago, we thought we were the absolute center of the entire universe. Understandable for their amount of knowledge at the time. But then in the 1500s, Copernicus came up with the heliocentric view of the universe, and that put the sun in the middle. And then Galileo was able to do the experiments with the telescope to verify that theory. And he was at least able to prove that the Earth was no longer the center of the universe by observing the moons of Jupiter. So the moons were definitely going around Jupiter and not around Earth. So that squashed the Earth is the center of everything theory. Then we're going to fast forward to the 1920s when Edwin Hubble discovered that there are galaxies outside of our own. And that just absolutely changed our entire scale of what the universe even is, and definitely put us no longer anywhere near the middle of it. He also discovered the cosmological expansion. This is an important concept. This is the observation that all the galaxies in the universe, except for one, are all traveling away from our galaxy. But it's not actually that the galaxies are themselves moving through space away from us. It's actually the expansion of space-time itself in the empty space between all the galaxies. Those areas are expanding, and therefore it's pushing the galaxies away from us. So that was bizarre, and that was such a surprise that everything was expanding. And astronomers needed to try to come up with some sort of reason for that. And then, so soon after, Georges Lemaitre, he came up with the Big Bang Theory, because he still needed like a starting point for life. He was a priest, and he was like, if everything just came from one moment, then we can still say like God created that moment or whatever. But he was right. So far as we can tell, the universe did start in a teeny tiny little spot and then has been exploding outward ever since. Then in the 1930s, very soon after that, Fritz Zwicky observed one of the largest nearby galaxy clusters. There's over 1,000 galaxies in this cluster. It's a pretty big one. And he was making just general observations, trying to gather some data, categorize things, just use all of his tools to analyze this galaxy cluster. And he was super surprised when he measured how fast the galaxies were moving. They were moving way too fast to actually all be in a cluster together. So like if you're on the Earth and you shoot a rocket into space, as long as you're going fast enough, you can leave the Earth and go to space. And there's an escape velocity for any gravitational bound collection of objects. So for all of the mass that he could see, he was looking at the galaxies and the gas and the dust and everything that he could measure. He was only seeing a certain amount of mass. But all of these galaxies were moving within the cluster way faster than the escape velocity of that mass. And so he worked the numbers backwards, and he was like, there's actually 5 times more mass here than I can see. So that was really surprising, and that was the beginning of dark matter, the theory of dark matter, which is still a theory because we have not figured out at all what it is. We've ruled out a lot of things that it isn't, but we don't know what it is. And then in the 80s, Alan Guth really developed the Big Bang Theory with like a big stride forward, and it solved all these problems in a really elegant way, and it's called the inflation theory. So very, very early in the history of the universe, like just fractions of a second after the Big Bang started, it went from so it was expanding, right? And it went from like an atomic nucleus size to a grapefruit size very, very rapidly. And then after that, it expanded at a relatively slower rate. And when you have this pop of inflation right at the beginning, it makes all of these wonderful coincidences happen in Big Bang works a lot better with our much more modern theory of cosmology, which now includes dark energy. So in the 90s, the Hubble Space Telescope was put up, and it was in part named after Hubble because he was just such an important astronomer. And we like to honor astronomers with our space telescope names, except for James Webb. It just got named after a NASA administrator. I'm not sure why that happened. But all the other ones, very famous astronomers. So Hubble went up. It was named after Hubble because he was a great astronomer, but also one of its primary goals was to figure out, was to test and experiment and observe the expansion of the universe that Hubble discovered, because we weren't able to very accurately measure the rate of expansion, and seemed pretty important. So it went up, and everyone, all of the astronomers assumed that the expansion was slowing down, because that's nice and comfy, and that means that everything's just gonna like settle down one day and be calm, and it's not existentially problematic. And then when Hubble went up, it made its observations, and the expected curve was like a very slow down curve. It was literally the exact opposite, and the universe is actually accelerating in its expansion. And to like if you're in your car and you want to accelerate, you have to give it some gas. You need to add some power and energy to your engine. Same thing in space. And so we realized that if the universe is expanding and accelerating. There must be some mysterious energy out there that's giving it that power to go faster and faster. And we have no idea what it is. Equal to dark matter, we like straight up have no idea. And our like best guess is like 200 orders of magnitude off. It's like really, really bad. Which I would like to start off my talk with these subjects just to remind you that we're scientists and we never know the whole picture, but we try our hardest to work on the small problems that we can, that will then hopefully, as we observe them, illuminate better questions to ask. We're always trying to ask better questions, and that's part of that creative thinking. So now I'm going to talk about space telescopes. To observe the largest scale of the universe, you need really powerful telescopes to be able to look very far out into space to really see that whole structure. And, oh gosh, hold on, sorry. And all of the universe is observed by humans in the spectrum of light. So we have eyeballs that see visible light, optical light, really, really, really well. And they don't try to see any other bands of light because we're specialized in this one band. There are many other bands of light, and each space telescope that we put up there, we have it specialize in a very specific band of light, so that it can do the best science in that specific way. And luckily, we've been able to send up a lot of space telescopes, and we've been able to hit all the main wavelengths of light at this point. So we have this really great picture of the universe that we've been creating over the last 30 years with these amazing space telescopes. So the wavelengths that I'm going to be talking about today, I'm going to give an example of what looking in that specific band of light will reveal. Just like how if, like, I'm not emitting any visible light, like I'm bouncing off the sun's light. But if you wanted to straight up observe a human, you would need to look in infrared light because we're warm and we are emitting that light. And it's invisible to us because we see in the optical, but if you were to see in infrared, you would see people glowing all the time. So different phenomena in the universe will glow in different bands of light, and they will not glow in other bands of light. And so they will be invisible in certain aspects and very well lit up in other ones. So we do need all these different space telescopes to actually see all the different phenomena. So X-rays are emitted by very hot things, including the clouds of hot gas in the center of galaxy clusters. Ultraviolet and optical light is the most common emission from stars and galaxies. It's not a coincidence that visible light is the light that our eyes see. That is the peak emission from our star. So it is most efficient to see things in the brightest light that our star sends to us. And our star the sun is very average. So that is a very average emission throughout the entire modern universe. Then infrared light is emitted by stars and galaxies in the distant universe. And microwaves are emitted by the absolute furthest distant part of the universe that we could possibly see. So to get near, mid, and far, we need to look in 3 different bands of light, and then to see interesting hot gas, we need to look in X-rays. So the MVP telescopes that are going to be highlighted in my talk are 4 telescopes that represent these 4 bands of light. So Hubble is optical and ultraviolet. Spitzer is infrared. It is now dead and will be replaced with the James Webb Space Telescope, but that hasn't made any discoveries quite yet. And then WMAP is the microwaves, and Chandra is X-ray. Chandra is such an amazing observatory. I wish it was as famous as Hubble. And we need to give credit to these space telescopes because they have been the essential tool that we've used to really refine our cosmological models and really understand the universe deeper. Without them, we just wouldn't have the power to see everything we need to see to test our models. Two more things. So telescopes are time machines. I'm sure you've probably heard that before. I'm going to explain it again briefly. Because the speed of light is finite, that means that from when the light is emitted to when it reaches the observer, there's always a delay. And the more distant an object, the more of the delay. And when you're looking out into space and you're looking millions, billions of light years away, you're seeing objects from their past. And there's no way to see that object in the present. You cannot skip over the speed of light. So when we make these amazing space telescopes, they have the capacity to look at the furthest reaches of our universe, which means they're looking so far back in time, and we can see the origin story of the universe. And as we look at closer and closer galaxies, we get to see the overall evolution of the universe. It's like being able to see the entire timeline all right out in front of you, which is very, very cool. And then one more thing is that there is a consequence of this cosmological expansion that I mentioned before. So if all the empty space is expanding and the light that we're trying to see from distant galaxies is traveling through that space, the path of that light gets expanded and the light wavelength gets expanded, so it literally changes color. And so what was once optical light emitted nearby will redshift into infrared light, will further redshift into microwaves. And so that's why we have those 3 main observatories, because as we look further and further out, the light that was emitted changes color. And so we have to adapt and make sure we see the full picture. And here's an example. I don't know if you can see any of these photos throughout the talk, so sorry, I'll try not to rely on them. But this is a composite image of like 12 different ways of looking at our Milky Way galaxy in the sky using different wavelengths of light. Some of them you would never even recognize it's our galaxy. And they all look totally different, and you can learn so much about all the different parts of our galaxy and the features and the phenomena by looking in all these different colors of light. So now that we have the tools to study the universe, let's talk about the theory and see how we apply the tools to these theories and test them. So there are 2 main components that make up this absolute largest cosmic structure. The smaller component is galaxy clusters that have a dark matter halo around them. And then on the larger scale, you have these dark matter filaments that connect all the clusters together into this giant web that encompasses the entire visible universe. And I will show you pictures, and it will make sense, hopefully. So first of all, galaxy clusters are dominated by these dark matter halos. And by a halo, I just mean there's like this fuzzy sort of cloud, because we cannot see dark matter. We can only see its effects due to gravity because it has mass. But it's completely invisible to light, so no telescope can actually observe dark matter. We can only observe its effects, but luckily we can observe the effects. And so galaxies have a dark matter halo. Pretty much every single galaxy has a dark matter halo, and therefore a galaxy cluster will have an overall really big dark matter halo. And here is a image from Spitzer Space Telescope of the Coma cluster, which is the one that Fritz Zwicky was able to discover dark matter within. Here is a picture of from Hubble. Hubble's just such an MVP. I hope we all have a little warm spot in our heart when we think of the Hubble Space Telescope. This is a Hubble image, and I don't know if you can see, but I'm going to try to just point it out for those who can. If you see, this is a big galaxy cluster right here, and there is a galaxy right here that is getting completely spaghettied out, and it's not that it's actually getting stretched and destroyed. It's the fact that this giant cluster is so heavy, has so much mass, that it is not just pulling in the stars and the galaxies around it, it is pulling in the fabric of space-time itself, and it's acting as a lens. So any object that's behind it in any way, its path to us, the path the light takes to us, is going to be curved, is going to be pulled on by this gigantic massive structure, this galaxy cluster. So based on based on the lensing effect, we can just measure how squished out a certain galaxy is. We can figure out what that lens must be, and we can figure out how heavy, how much mass there is in the cluster. And again, with this method, we see that there's about five times more mass than we can visually account for. Next one is bright X-ray gas. So in this photo, there is no like central glow because this is taken with an optical image from Hubble. In this image, I don't know if you can see it, sorry, there's a giant purple glow in the middle between all of these galaxies central in the cluster. And this is looking in X-rays. This is from Chandra. And there's very, very hot gas in the center of these giant galaxy clusters. And it's so hot that it's not glowing in infrared like us. It's not glowing in optical or UV. It's glowing in X-rays. It is super, super hot. And based on the heat, we know how much energy each little molecule of gas has. And from that, it's a similar escape velocity thing as before. So if it has enough energy, it should be able to escape the cluster. And based on how hot this gas is, we can measure how much gravity must be there to be able to hold it in. It's because it must have less energy because it's all clumped up in there. It's not leaving. So another estimate of how much mass is in a cluster. This also agrees with the 5 times too much. So even though we cannot observe dark matter directly, we've come up with 3 separate ways to measure it, and they're all in agreement with each other, which feels good to be able to figure that out, even though we literally can't see it and we have no idea what it is. So there's another sort of evidence for dark matter. It's not like as direct with this 5 times. It's not like confirming the 5 times thing, but it is interesting to note because in a galaxy cluster, there are the galaxies and then there's this intra-cluster gas that's in between all of them. And it turns out that this gas actually accounts for more mass than the galaxies themselves. So if you were to ignore dark matter and measure the galaxies and their mass and then the gas and that mass, you should be able to figure out where the center of mass is for the entire cluster. This, I don't know if you can see it, is the bullet cluster. It's a super famous 2 clusters of galaxies just rammed into each other, but because galaxies are pretty far apart from each other, it's not like the galaxies really rammed into each other, they actually passed right through each other. But all of that intra-cluster gas was kind of diffuse and evenly distributed, and so the gas actually did slam into each other. So you have one galaxy cluster going through and another one going through, and then in the middle you have all that gas. And we can observe with our different types of light, we can see the galaxies over here and the gas is in the middle, and then we can use our methods from before to figure out where all the mass is, because if it's lensing, it's going to be lensing from a certain area. And it turns out that all of the mass, like the majority of the mass, is not concentrated where the gas is, it's concentrated where the galaxies are, which is weird because we know that the gas is more massive than the galaxies. So from what we can see, we would assume that the center of mass of the whole system should be with all the gas, but it is not. It is over by the galaxies. So there must be some extra mass in there that's traveling through with the galaxies. And that's more evidence for dark matter. And this bullet cluster is as a single example, is the best example for best proof that dark matter has to exist. And so from what we can see, galaxy clusters are these giant, dominant, large-scale structures, and they have a dark matter halo not only around each galaxy but around the entire cluster as a whole. This is the Hubble Ultra Deep Field. If you don't know what that is, I would love to tell you about it. It is such an epic photo. The Hubble Space Telescope has a director, and the director always has his own discretionary time to look at something amazing because he earned it. And one year, the director was convinced by a group of people to use his discretionary time to look at the darkest spot in space that we had yet found, like the most empty spot, and look at it for a week straight and just see what happened. And turns out that there are just so many galaxies in the universe, and in this teeny tiny dark spot, there were tens of thousands of galaxies. And this was just with Hubble, which is only going to catch the nearby galaxies. It's not even going to see the really distant ones. So we're doing follow-up deep fields with other telescopes in other bands to really just catch a glimpse of how deep our universe really goes and how much is in there. So I've talked about the dark matter halos around clusters. Now I'm going to talk about the dark matter filaments that connect all the clusters together into a giant web throughout the universe. One sec. So the dark matter filaments are a theory that is based on the fact that we have such great evidence for the dark matter halos around the clusters. We're trying to extrapolate and see what's connecting all the clusters. And we have lots of simulations. I hope you can see this. It's very cool. This is a super famous simulation of the observable universe if we could see the whole thing in real time, if we could see all the way out to the edge how it is today. And if you can see, there's this amazing webbed structure. It's pink and purple. There are these dark voids where there's very, very little, like the most empty space ever. And then there are brighter spots where the galaxies are more clustered together and where the density is greatest, and where filaments connect to each other in this web. The nodes where they connect have the most mass and are some of the hottest places because they have so much mass and gravity that they can hold in so much hot gas. Then there was a follow-up experiment to this same simulation where they reprocessed it with some new information and then zoomed in on that central, most bright portion. And it turns out that if you zoom all the way in, you just get a gigantic elliptical galaxy, which is what we see when we look at the center of the biggest galaxy cluster. So it was like, oh, cool, works out. Oh my gosh. So we have this idea of these filaments that we have developed based on our observations, but how did these filaments develop over time? What did they start out as, and why are they filaments now? Have they always been filaments? What is the history of our universe there? So we can observe in all those wavelengths of light from now till the past and see if we can trace back these we call them overdensities, where there are certain areas that have more mass than average, and there are certain areas that have less mass than average. And the filaments with all the dark matter and all the galaxies are the areas with overdensities. So let's see if this movie will play. I genuinely don't know. Where's my cursor? Oh. Is it going? Okay. So I'm going to play it a couple times. I'm just going to let it play this time. Okay. So now that you saw that, let's do it one more time, and I'm going to explain what's happening. So this is very early universe. Everything, all the matter is very evenly distributed with only minor fluctuations in a little heavier here, a little less over there. And then as you play the movie of time forward, gravity is the winner in the areas where there's a little bit more mass, and gravity's going to pull in a little bit more there, and it's going to pull in wherever all those slightly more dense areas are, and it's just going to pull the matter towards that and away from the areas with slightly less. And I'm going to play it one more time so you can see. So it starts to clump up, and then you see these filaments connect to each other. Super cool. I love it. Okay. So when we look as far away as we can with our microwave telescopes, we can see the absolute edge of the visible universe. Before then, the universe was actually opaque, and you cannot see past this spot. So this is the oldest light we can see. It's from about 300,000 years after the Big Bang, and it's redshifted all the way to the microwave. And here's just an example of an older space telescope that was observing this phenomenon, and then a newer one with much better resolution. So this was COBE, and this was WMAP. This was still revolutionary at the time, but this was much better. So when we observe the cosmic microwave background, it is this microwave radiation that's coming from every single direction in the sky, and is almost completely the exact same temperature everywhere. But we can see that if we get the resolution with these wonderful space telescopes, we can see the very, very minor fluctuations in the temperature of the universe at the time. And when we measure how like the distribution of all of these little fluctuations, it totally matches up with our model of how the mass seems to be distributed. So that's nice. We have our modern image of the universe, and you can extrapolate it all the way back 13.8 billion years, and it totally matches up. So also feels nice. But the filaments, we actually can't observe them like we were able to observe the dark matter in the galaxy clusters, in those halos. They were pretty concentrated and packed in with the cluster. The filaments that connect the clusters have much less dark matter, and so they aren't prominent enough for us to be able to really see that lensing or that bending of space. So we just got to do our best and try another way. So if you can see this image, it is a Hubble image of many, many galaxies in a very wide area of the sky. And in the top part of the image, there's not very many galaxies. They don't look correlated. But in the bottom part, there's this very wide band of a lot of galaxies that are all very dynamically interacting with each other. They're all gravitationally linked to each other. And this is in the exact shape and dimension of a filament. So even though we can't see the dark matter, we can see its effect on shaping where these galaxy clusters are being directed through space on these grand scales. And by the way, so this image is pretty for us, but I just wanted to show you what the scientists actually see. They don't look at the pretty pictures. They extract data from them, and they make nice little charts. So all of these data charts came from this observation. So there's more than just light coming at us. There's so much information embedded in that, and that's how astronomers get to do so much. It's not like they're just looking at pretty pictures all day, although that would be nice. So thank you all for listening. I have covered an introduction to cosmology, right? How we think about the universe on the grandest scales from the beginning till now to the future. I reminded you of how far we've come from our Earth-centered ideas. And I talked about how space telescopes are so amazing and really help us push our modern cosmology to its limit, and then these cosmic structures, these largest structures, are dominated by dark matter. They clump together with the galaxy clusters, and they even connect all of the clusters in this giant web that extends out throughout the entire visible universe that can be traced all the way back to the Big Bang. So I hope you followed that. Thank you so much for your attention. And if there's any questions, I would love to take your questions.